You go down to the pad, make an announcement. Oh, let's see, the first announcement is the midterms are pretty much ready. So they have to be recorded, and I guess we'll do a final check on them and stuff. But I guess they'll be ready for pickup this afternoon. And make sure you get solutions. So make sure you get solutions. And by all means, check yours against the solutions and make sure you understood everything. Actually, they were quite good. So we were very pleased with them. Okay. I don't know. What did you think about the midterm? Wasn't too bad, was it?
Reasonable.
Yeah, I thought it was pretty reasonable. Oh well. I think maybe some people in SITN are taking it today, so I think we can't go into detail. But okay. I guess last time we were looking at transfer functions and convolution systems, and we looked at impulse response and step response, and these are both quite important ideas. Impulse response is, of course, there's many ways to think of it. First of all, when you look at a convolution system, it's simply this thing here. It's the convolution kernel, or there's various names for it. I guess in engineering, it's almost universally called just the impulse response. It's called the impulse response for the following obvious reason. If you put an impulse into the system, this is what comes out. What's really interesting about that is if you have a system described by a convolution or transfer function, and you walk up to it, and you apply an impulse, so a very large, brief duration signal, it will do something. That'll be the output. And the point is that simply by recording that, you now have total predictive ability for that system for any other input. In other words, any other input, you can immediately figure out what's going to happen. Not only that, once you've got a feel for sort of an idea of what an impulse response does, you can even say a lot of things intuitively about what it's going to do. In other words, if the impulse response is kind of flat for a while, doesn't do much, and then all of a sudden goes up like that, you know what you have here is that there's going to be a delay. Okay? If the impulse response immediately does something and calms down very quickly, what you have is a fast system, that whatever it does, it has a very short memory and it does it quickly, this kind of stuff. So you'll get that idea. Step response is, of course, just the response when the input is a step. And this is very, very widely used in lots and lots and lots of systems. It is probably more widely used than the impulse response. Although it's hard when you see a step response to figure out immediately what the system does, or at least it's hard for me. Anyway, the step response is actually widely used because a lot of systems have input signals which are modeled as steps. And let me just give you some examples. There are a lot of electrical systems where a voltage will swing from 0 to some value, or a current will swing from 0 to some value. And then it just takes a while for the system to react. There's many systems where this is the case. So step response is pretty common. It's very common in chemical engineering to look at step response. Step response refers to, for example, what would happen to the pH in some solution if you turn on a pump that pumps some chemical into a reactor tank and let it keep pumping. Then the step response is what you're going to see, the step response from that reactant flow rate to the pH, for example. So it's pretty common. Step response in an airplane or something like that, the step response to, say, altitude with respect to pitch or thrust is just what it sounds like. You bump the engine, you bump the thrust up a little bit, and then you see what happens to your pitch or your altitude or something like that. That's the step response from thrust to altitude, say, for example. So it's very, very common. Of course, it's nothing more than the integral of the impulse response. It's nothing more. And vice versa, the impulse response is simply the integral of, is the derivative. To get the impulse response, is the derivative of the step response. Now, if you apply a constant input and the system is stable, then this integral here makes sense. This is what the step response will converge to. Integral from 0 to infinity h of tau d tau. It also happens to be precisely the transfer function evaluated at s equals 0. And this is called the DC or static gain. So static gain is probably the more sophisticated term. DC has rather a cool, it's kind of a retro term here. So people haven't used this seriously since maybe, I don't know, 1959 or something. And so, but it's, I don't know, it's very, it has a good retro sound to it, right? It was when people were talking about AC and DC, so you can, I like it. I use it just to irritate people and stuff. Okay, so what it is what the step response converges to, is what the DC gain is, or the static gain. And there's lots of rules. They're fairly obvious, and you can sort of figure these out. But for example, to find the DC gain for a circuit, what it means is that every signal in the circuit is constant. So if an inductor has constant current across it, the voltage across it is 0, so you short it. That's what it means. It's a wire. If you have a constant voltage across a capacitance, that can only happen if the current into the capacitor is 0. So you open circuit all capacitors and so on. These are basically rules from 101. If you have a system of algebraic and differential equations, to say that all the derivatives, or that the system is in static equilibrium, says that every signal is constant. That means you just set all the derivatives equal to 0 and proceed, right? So that's the idea there. And for a block diagram with, for example, integrators in it, what can you say about an integrator if the system is in static, steady state? If a ramp, that doesn't sound like static to me. Yeah, so if the output of an integrator is constant, what can you say about the input? What's the input of an integrator? If I show you a big block diagram and tell you it's in steady state, what's the input to an integrator?
0.
It has to be 0, period. Because in fact, the input to the integrator is the derivative of its output. If the output is constant, the input is 0. Okay? If you have anything non-zero going into an integrator, the output will ramp. But that's not allowed. It's static. So in a big block diagram, you simply take every integrator and you make the input 0. And this will give you the static steady state or DC analysis of it. Okay, so let's look at some examples to make these ideas of impulse response, step response, and DC gain to get a physical feel for them. So we go back to the vehicle suspension example. So it's the transfer function from the road to the vehicle height. It's given by the second order differential equation. Here's the transfer function. Well, the mass, damping, and stiffness are all positive. So the roots, this is stable. Both roots of this are in the left half plane. The DC gain, how do I get that? I plug in S equals 0, and if I do that, I get K over K, which is 1. Actually, that's completely obvious physically. In other words, if you have an auto or something like that, and you run over a bump, that's a curb, right? That's basically with a step input. What happens is it hits the curb, and it bounces up and down depending on the damping and all that kind of stuff. But eventually it settles out, and it settles out to a height above the road that's equal to what it was before. Unless unless you hit it so hard that you actually do have plastic deformation in your suspension system, right? But if you don't do that, it will settle out to the same height above the ground, and that means, of course, that the DC gain is exactly 1. If you bump over a curb that's 6 inches high, and you wait for everything to settle out, you will, after everything settles out, the vehicle will be 6 inches higher than it was before it hit the curb. Obviously, that's its DC gain is 1. But you can also see it just by plugging in S equals 0. Here, you get the same thing. So that's what the step response gives you. It's now a way for you to visualize it. It's basically the response after you hit a curb. So here's the step response for unit stiffness, unit mass, and 0.5 damping. That's underdamped. I think you can see that very, very clearly from this response. And you can see here that if you hit a curb that has a height of 1, some units, then in fact what will happen is you'll actually go up 50% higher than that, right? Because what happens is you hit the curb, it compresses the springs, and then the springs then they do their thing. They let go, and it accelerates the car. And when the car gets to the right height, it just keeps going because of the inertia and so on. So this is the idea. And it settles out because the damping sort of removing the energy of bumping over the curb. So that's that. And you can even imagine what this would feel like. The answer is probably not so good. Right? That this is not, you probably wouldn't imagine this to be a comfortable ride. I randomly picked these units. They don't have anything to do with real time axes. But here, it takes about, I don't know, 10, 20 seconds to really settle out here. Okay. On the other hand, if the damping is 2, this is critical damping, because this is, if you can just read this off now. In fact, you should start recognizing this. This is s squared plus 2s plus 1. That's s plus 1 squared. That's critical damping. So for critical damping, here's what the step response looks like. And it actually looks pretty good. It does, in fact, overshoot about 15%, which you can see very clearly here. So when you go over a curb with critical damping, you overshoot about 15%. But you settle very quickly. Basically, in 6 seconds, basically you've converged to the new height of the road, and so on. Now, just for fun, what do you imagine this picture looks like if we are way over damped? What if B were 10? What do you think? What would this look like? What do you think? What would this picture look like if it was 10? Well, first of all, if B is 0.1, what would happen? That's even less damping than this underdamped case. What do you imagine this would look like? Yeah, this would in fact be going like that, and it would take a long, long time, right? If B were 10, if the thing becomes overdamped, what do you imagine the step response looks like then? Got 2 exponential terms. What do you think? Yeah, actually it would have a kind of a bump like that, a rapid bump, and then it would go like this, right? And in fact, if someone put a requirement that you don't overshoot at all, then in fact you probably want something that's slightly overdamped. Okay? So this is but it might look something like this and just take a long time to get there. Okay? So, and what you'd have here are you'd have 2 poles, both real. One would be relatively fast, that would be this one. And one would be relatively slow, that would be that. And this is the kind of thing you'd see. Right? So in fact, the disadvantage here is you'd get a bigger shock as you go over the curb. That's the first thing you'd notice. The second thing you'd notice is it would then take a lot longer to converge to the ultimate height. Okay? So that's just a rough idea. Okay. Let's look at another example. This one's from circuits. So here, we can imagine this is in fact a small wire, and we're looking at time scales so fast that we have to actually take into account the capacitance of the wire, the capacitance to ground. And so here, a common model of a wire might be as a bunch of RC segments. So here's 3 RC segments, a 3 RC segment approximation of a wire. I guess in 141 or something like that, you'll actually study the PDE that describes a wire, and this will be an approximation of that PDE. So here you have these 3 RC segments, and you can immediately get some rough idea of what's going to happen when the voltage here. If we look at the step response, for example, well, we can first work out the transfer function. The transfer function of this is, after a fair amount of algebra, I mean, it wouldn't be that hard. I guess what you do is you work out the impedance of this, then you kind of put it in parallel with the impedance of that, in series with that, in parallel with that, in series with that, and you end up with the whole impedance. Then you kind of go back and you do various voltage divider things and so on and so forth. But what you'll end up with is this in the end. That's the transfer function. So here's some obvious things. If I plug in S equals 0, I get the DC gain, and it's 1. Does that make sense here? It's the voltage transfer function from here to here. If this voltage is constant, and all voltages are constant, what's the voltage here? It's equal to that, because there's no current flows. So that's completely obvious. All right. If you look at the poles of this, that's a cubic. You can work out the roots. The roots are -3, -1.5 about, and -0.2. Okay? So that, again, it kind of makes sense. Which of these roots is going to give you a rough idea of how long it takes for this circuit to react. In other words, when I put an input signal here, how long will it take before Vout does anything? Just order of magnitude. It's going to be determined by this, right? This says that the impulse response of this wire is going to have a term that looks, there's one term that's e to the minus 3.2 t, and that's all over in, if you take 5 time constants, that's all over in 15. Did I get that right? No. 1 point something or other, right? In about 1.3 seconds, right, or so, 3.2 times 1.3 is 5. If I'm just using this rough rule of thumb that 5 time constants is kind of, that's it, right? So you're out in 5 time constants. That's actually, that's what it takes for an exponential to go down to about 1%, right? So this has got something, this corresponds to an exponential that kind of decays on the order of a second or so. This one is one that decays on the order of 2 seconds, let's say. And this one decays on the order of, I don't know, well, I guess more than 20 seconds, 30, 40. No, sorry. 1 time constant would be 20 seconds, so maybe on the order of a lot, 80, something like that. So this is 80 seconds. So this is the one that really drives the time constant of the whole thing. And in fact, it's interesting to kind of get a rough idea. There's a bunch of, if someone showed this to you and asked you what are the time constants, he was up all night, actually. I'm not sure what he was working on. He hasn't slept. It's all right. He won't. Oh, he's awake. It's okay. What were you working on? What were you working on? Oh, no, you don't have to tell us. Of course, I just assumed it was research or something, but if it's something else, that's okay. We'll just get right back to RC segments. That's fine. Yeah, okay, RC segments. Back again. All right, so the step response here is actually no surprise. Here it is. If you look at it, I guess if you looked at it casually at first, you'd say, okay, well, that's just a, you'd have to look at this very closely to realize that this was not just something from 101, which was an RC thing, right? But look at this. It takes about, as we guessed, about 20, 25 seconds to be fully converged, something like that, right? And if you want to see the real difference, you'd have to study way down here to find out the difference, right? What you'd find is it's a lot flatter there. And physically, why would that be here? What it says is that compared to a circuit that was just like an RC circuit like this, right? It says that when the voltage here pops up, the voltage here is actually, for short times, a lot less. Why is that? Just physically, just describe intuitively. Exactly, right. That physically what happens here is this capacitor doesn't charge at all until it's charged by the voltage here. So this guy doesn't even start to charge until this voltage rises. This voltage doesn't rise until this capacitor charges. That doesn't happen. This only charges when the voltage here rises. Okay? Voltage here rises, well, that starts rising immediately, right? So the voltage here would look, for small times, it would look like this. It would start going up like that. The voltage here would be like a quadratic here, because this guy's starting to go, and then it would start charging it, and so on. And then this guy actually looks like a cubic, which is very flat for small t. And in fact, what do you think is going to happen to you in 141 when you write down the PDE that describes this? What do you think actually happens in a wire when you pop the voltage up like this? What actually happens over here? What happens is the output voltage is really, really small. In fact, it's dead zero for a certain amount of time. What amount of time? Speed of propagation of the wave down the cable, right? So that sort of fits the intuition. Okay, so this is sort of the idea. Okay, what would the impulse response of the wire look like, by the way? What does the impulse response of the wire look like? What do you think? You can just differentiate this. Most of it's done by here, so it might look something like this. It would have its kind of its maximum around right there, so it would rapidly rise, and then it would kind of fall like that. It might look something like that. That's the impulse response. I'm just differentiating this. I mean, if I didn't do it right, that's fine, but it looks something like that. That's the impulse response. And then, again, this picture, what this tells you is how much the output of that wire depends on what the input was various times ago. So it says, for example, that for, if I ask you how much does the output depend on what the input was, let's say 0.5 seconds ago, the answer is very, very little. Okay? If I ask how much does it depend on what the input was maybe 3, 4 seconds ago, the answer is a lot. The overall memory of the thing is maybe 20, 30 seconds and so on. Okay? So that's kind of the idea here. Okay. Okay, one of our last topics is the idea of peak gain. We'll do this quickly. It's kind of, I won't get into all the details, but it's actually definitely worth knowing about. So here's the basic idea. You have a convolution system, you have an input signal and an output signal. And basically you want a rough idea of what is the gain of that system. How big can it magnify system? I mean, a signal. How much? Well, one measure, of course, is the DC gain. That tells you if you put in a constant input of some magnitude, then the output will get magnified by 3 or minus 7. Okay? But the question then is, I don't know, what's a good measure for this? One measure is to take the ratio of the peak of the output to the peak of the input. Right? That's a reasonable measure of gain or amplification factor or whatever you want to call it. And it turns out that this number here, the peak of the output divided by the peak of the input, turns out it depends, of course, on the input you put in. It depends on the input. It can be low, it can be high. In fact, it can be all sorts of numbers. So if you want to look at the maximum gain, in other words, you find the input signal whose peak is amplified as much as possible by a system, it turns out we'll be able to identify exactly what it is, and this ratio is given exactly by the integral of the absolute value of the impulse response. That's what it gives you. Okay? And it says then that if you have a system and you figure out what the impulse response is and you work out this integral, that number tells you how much the maximum possible amplification factor of a signal is, measured in terms of peak. Okay? And it's easy to work out, to verify this. I mean, it's just to use a couple of properties with integrals and absolute values. Y of t is this thing, and so the absolute value is that. And whenever you put absolute values inside integrals, you increase the value of the integral, right? Because an integral is like, in fact, it's a sum. It's like a sum. And if I take a sum of things and put an absolute value inside and then put the absolute value in each term, I increase everything. Oh, except in what case? When would it be that the absolute value of a sum equals the sum of the absolute values of some numbers? When would that be true? Yeah, when a bunch of numbers are all positive, then the absolute value of the sum is the sum of the absolute value. What if they're all negative, by the way? Then it's also equal, right? Because the sum of the absolute values is the same as the absolute value of the sum. If they have mixed signs, then the sum of the absolute values is always larger than the absolute value of the sum, because you get some kind of cancellation. That's all it is. So the same is true here. I pop this inside like that. Now I use the fact that this thing, I don't know what it is, but it's certainly less than the peak of u. Okay? And then I get the integral of the absolute value. So this basically explains that. And to get an input signal that suffers an amplification factor that's near this, what you do is you pick a large T, and you basically arrange, what you do is you go back and you do the analysis and you ask, when would this absolute value of the integral equal the integral of the absolute value? And the key there is that everything in here has to have the same sign. So u of t minus tau and h of tau have to always agree. If one is positive, the other should be positive, and vice versa. And what that says is that u should equal, it should be a signal, which is either plus or minus 1, depending on the sign of h of t minus t. If you do this, the peak of u of 1, and if you work out what y of capital T is, it's integral of the absolute value. And if you pick t large enough, that's very close to the peak, to this thing. So this is the idea. So that's the idea of the peak gain. It's actually quite a useful idea, and we'll look at it in a minute to see how that works. Here's an example. It's a transfer function. It's 1 over s plus 1. That's probably one that you should just memorize and understand what it does. Its impulse response is e to the minus t. And some people call this an exponential smoother or a forgetting factor. There's all sorts of names for this. Many fields have a name for this. It's used in finance. It's used in lots and lots and lots of fields for just basically a convolution with e to the minus t comes up. It's basically first order forgetting factor or discount factor in economics, right? Okay. So the DC gain is 1, and that says constant signals are amplified by 1. To calculate the peak gain, we take the integral of e to the minus t d tau, but this thing is positive, so I can just remove the integral, the absolute value signs, and you get the same thing. That says that for this system, the peak gain is 1. In other words, that the peak of the output signal is no more than the peak of the input signal, and in other words, a constant signal is amplified by as much as any signal can be amplified. That would be this. So in fact, in the general case, it turns out that the peak gain is equal to the DC gain only if the impulse response has constant sign or if the step response is monotonic, meaning it only goes up or down. It can go down, that's fine. But if the step response only increases, it goes up. And let's do to see if people get this, let me just quickly do an example here. Suppose I have two systems. In fact, suppose it's a suspension system. It doesn't really matter. And I have in one system, I have an active suspension system, and when I turn the active suspension system off, the step response looks like this. Okay? When I turn the active suspension system on, it looks like that. These are the step responses. What can you tell me about the peak gains of these two? This actually requires a bunch of thought. What can you say about the peak gains of these two? If I put in a constant, in each case the gain settles out to, let's call it 1. Okay? So what's the peak gain of this system? The first thing you have to do is work out the impulse response of this and this. How do you get the impulse response of this? You just differentiate, right? So the impulse response of this thing, I don't know what it looks like, but I'll make it up. Say it looks something like that. That's the impulse response. And now you take the absolute value and you integrate. But wait a minute. You take the absolute value of this and integrate, you just get back this signal. And you get 1. So the peak gain of this thing is 1. This says that no matter what weird signal you put in here, no matter what it is, when it comes out the other side, the peak of the output is no bigger than the peak of the input. What is the impulse response of this thing? Well, it must look like this. So let me see if I can get it right. It's 0 there. So it must look like this. It's got a big bump, and then, let's see, there's another one. There's a 0. I don't know, something like this, right? Okay, well, you get the idea. It looks like that, right? It's the derivative of this thing. Now, if I integrate this whole thing from beginning to end, what number do I get? If you integrate this impulse response along here, what number do you get? 1. And that must be because the net area, that sort of positive area, then negative, positive, negative, positive, negative, and so on. It must be that the total excess of positive over negative is 1, right? Now, if I take the absolute value of this thing and integrate, what's going to happen? What happens when I take the absolute value of this thing and integrate it? Oh, you're going to get a lot more than 1. Because what's going to happen is you get a big contribution here, right? Then you have a big contribution here, but it's not subtracting now. It's being added. You take the absolute value of the area. So you take the sum of the areas of this, and you're going to get a number probably around 3 or 4. And what it says is that there's two bad things about the system. If this were a suspension system, there's two bad things about it. The first is that when you go over a curb, the whole thing's gonna vibrate for a while, which is not good. But what this says is there's some sequence of curbs you can go over where the response of the thing will actually be extremely large. It'll be 4 times larger than the size of the curb you've gone over. Just intuition. What would be a very bad thing to drive over in the suspension system? Just guess. What do you think? A curb? What would it be? Yeah, speed bumps. And how would they be spaced? Yeah, they'd be spaced just like this. If you drove over speed bumps with this thing, and they were spaced just like that, what would happen is, of course, this would be like a swing, and you'd be pumping a swing. You'd go over the speed bumps, each of which is only 10 centimeters high, and out the other end, you'd find yourself with swings up and down that are 40. Okay? So, and again, we get this all just from impulse and step response and stuff like that. And I guess that makes perfect sense, right? If you have an underdamped mechanical system, and you walk up to an underdamped mechanical system and then shake it right at about the resonant frequency, of course it's going to be amplified by a lot. And that's, so all of this we just got directly from looking at this, okay? But we could for example, I don't know, on a homework problem or something, I don't think we have, but on the homework problem we could certainly ask for actual numbers here and ask you to reconstruct the worst possible types of speed bumps and all that kind of stuff. But you get it all from here. Okay. Okay, our last topic on transfer functions is, it's kind of vague, and so let me, but it's actually very interesting. It's about linear time-invariant systems. So suppose you have a system which is linear, so that means superposition holds, and it's time-invariant, and that means it commutes with delays. So that means that if you have a system and you put in a signal and you record the output, had you put the signal in later or earlier than that experiment, the output would have been the same, only shifted the same amount of time. So that's all it means. Oh, this is, some people would be annoyed by that. Fortunately, not us, right? Okay. So it turns out that any convolution or transfer function system is linear and time invariant. That's observation number 1. Then basically, depending on how careful you want to be, the rough statement is this, is that any linear and time-invariant system is given by a convolution system. Now the problem is, to actually make that into a correct statement is, it's not fun, and it gets very technical, and there's many ways to say it as well. Right? So I don't know, it just gets kind of ugly. But it's certainly something you can take to be more or less true. It's more or less true except for pathological cases that you will never, ever see. So, and what this says is that the idea of a convolution and transfer function, it gives a universal description for linear time-invariant systems. It's actually an amazing fact, and it basically simplifies a lot of things. Here's an example. If you take, I don't know, take acoustics or electroacoustics, right? So you put together a system that consists of an electronic amplifier, a loudspeaker in a room, and then a microphone somewhere at the back of the room. And then you consider the following system. The input is the input voltage that drives the power amplifier, which then drives the speaker, which excites all of the, all the air in the room is now moving from this loudspeaker. And in particular, the air right in front and in back of that microphone at the back wall is moving a little bit, which produces small electrical signal coming out the microphone. So that's a system. Well, it turns out it's linear and time invariant. And you can either know this or you can check with people. You can go to the person who built the amplifier and say, is it LTI? And they'll say, sure it is. Well, unless you put in an input voltage more than 3 volts, it is, because then the amplifier clips. And you'd say, okay. And then you'd go to the loudspeaker manufacturer and you'd say, is it linear? And they'd say, sure, we spent a lot of trouble making it linear and time invariant. They said, actually, that's not quite true. If the voltage gets up to 30 volts, you probably generate about 1% distort. It's about 1% nonlinear, but it's close to linear. And then you go to someone who knows acoustics, and you say, if I wiggle the air at one end of a room, and I look at the effect at the other end of the room, is that linear and time invariant? And they'll say, yes, unless the wiggles are so high they're from, say, you know, from an explosive detonation or something like that, or whatever, you know. I mean, because then you get into nonlinear acoustics. But they say if the sound pressure level is less than 130 decibels, it's pretty close to linear, actually, right? And so what that means is that this whole system is in fact linear, and in fact all you really need, linear time invariant, it means all you really have to do now is measure the impulse response. Okay? If you measure the impulse response of that system, you can now go back and, you know, with MATLAB or any whatever you like, you can actually now simulate the effect of that system for any other input. For example, your favorite music can be played through it, and you will find out exactly what it would have sounded like at that point. Okay? So this is sort of the idea. It's really very impressive. It also says, I mean, it's as impressive there. After a while, you get used to it. People are no longer impressed by this fact. But the fact is, if you really think about it, you should be very impressed. Another example, just to give you another example, would be just take someone with an airplane or something like that. So you have an airplane, and you say, we're going to do just one test in this helicopter. I want you to simply, what I do is I have accelerometers, so I'm instrumenting the motion of the helicopter, and I'll say, I just want you to bump the thrust up for a second or two, and we'll record the altitude or whatever. Doesn't make any difference, right? Your pitch rate or your altitude doesn't make any difference. You just bump it up. The pilot does it, and the thing starts climbing like that, and then you say, okay, that's enough, thanks. You now have the step response. You can differentiate and get the impulse response. And now you can pose all sorts of questions. Like you could say, you could ask questions like, what if you put in this input signal? How would the helicopter have reacted, and so on and so forth. And you'll be able to predict these. Your predictions will be good, provided the assumption that everything's linear and time invariant is accurate. Okay? So you can go back and do all sorts of simulations, and you could even then work out, for example, the optimal thrust trajectory to pull a helicopter up fast or something like that. These are things you could work out. Okay? So it's all pretty impressive. After a while, people don't even notice it anymore. They just assume everything's linear and time invariant, and they just give you transfer functions, and people say, well, everything is, so what, and so on. So, okay. Any questions about that? But this is why it is so universally used. Okay. Our next topic is the idea of sinusoidal steady state and frequency response. And let me say at the outset that we're actually not going to do anything new here. This is just consequences of what we've been doing. In fact, if you think about it, I guess we didn't do anything new in the last lecture either, right? We were just studying convolution systems. And we looked at impulse response, step response, so on and so forth, just interpreting it. Here, same thing. There is absolutely nothing new. This is just convolution systems, and if people were smart enough to look at a convolution integral and understand it immediately, you wouldn't need any of this, right? So, okay. So the idea now is to tie together convolution systems and transfer functions with what you know from 101, which is having to do with sinusoidal steady state. And it's very simple to do that. What you do is imagine you have a convolution system here, and you apply a sinusoidal input. Well, what will the output be? And the first guess would probably be, well, the output is sinusoidal. Turns out that's false. That's not true. What is true is it turns out the output converges to something sinusoidal. So we'll see how that works. So you put this input in, which is cosine, and I write it as a sum of complex exponentials. And the output then is you just plug it into the convolution integral, this, and now I'll replace the cosine with this. And I can rewrite this thing. I'm going to actually rewrite this in an interesting way. First, it's the integral from 0 to t, and I'll write that as the integral from 0 to infinity minus the integral from t to infinity. Well, the reason is that this term here is going to turn out to be sinusoidal. In fact, this is a very interesting term. This is actually sort of what the output is if the input had started infinitely long ago. That would be this. Okay. This term here, which gets smaller and smaller as t grows, is the difference between this is the actual output, and this is what the output would be had the input started infinitely long ago. This is the difference, and this is called the transient solution. And that term, transient, is based on the fact that usually we consider stable systems, and so this actually decays with time. It can also grow with time, but that's another story. So if this thing, if you now work out the sinusoidal steady state response, it's this integral. Now I'm going to plug in cosine for these exponentials here, and I get this. It's this 1/2. That's this term plus 1/2. That's this term, and now this thing here. What I've done is I've taken the e to the j omega t minus tau. I took e to the j omega t outside because it doesn't have anything to do with the integration variable, which is tau, and it went here. E to the minus j omega tau, that's inside the integral sign, and I get this. Now, if you stare at this long enough, you'll realize that that's something you've seen. This is basically this is integral h of tau e to the minus s tau with s equal to j omega. That's what this is here. And so this term is equal to 1/2 e to the j omega t times h of j omega, and that's 1/2 e to the minus j omega t times h of minus j omega. And this is the same. I can write this several ways, but here's one. That's the real part of the transfer function evaluated at s equals j omega times cosine minus, and then the imaginary part times sine. Or I can write it as a cosine omega t plus phi, where a is the magnitude of this, and phi is the phase of the convolution system, of the frequency response evaluated at s equals j omega. In other words, we have an amazing fact here. It says that if a convolution system is stable, then the response to a sinusoidal input is asymptotically sinusoidal. And, even more interesting, well, it's at the same frequency. And the magnitude and phase come directly from the transfer function evaluated at s equals j omega, which is called the frequency response of the system. Comes directly from that. Right. So that's sort of the idea. And that gives you an interpretation of the transfer function evaluated at s equals j omega. The magnitude gives you the amplification factor for a sinusoid of that frequency. Okay? So that gives you a sinusoid, the amplification factor for a sinusoid of that frequency. So if, for example, h of j omega, when I plot it as a function of omega, and it looks something like this, right? And we'll see that, in fact, you can have something like that. The interpretation, let's call that 1, and let's call that 2. The interpretation is this. If I put in a low-frequency sinusoid into this box, what comes out asymptotically? What comes out? Well, if it's low, it's 0. The magnitude is here. The magnitude gives you directly the magnitude of the output sinusoid. And what is it here? 0. It's 0, right? So it says whatever this box is, when you put in a very slowly varying sinusoid, the output is basically 0. So in other words, whatever this box is, it doesn't react very much to slowly changing signals, right? On the other hand, if I put in a sinusoid with 1 radian per second frequency, this thing, it reacts considerably. It has a considerable reaction. If I make it 1.5, much less. And if I make it 2, it also reacts considerably. If I put in a super high frequency sinusoid, in other words, a sinusoid that's rapidly varying, what is the response of the system to this? It's very small, exactly, right? So in other words, this is yet, well, I guess I'm sorry to say, but this is yet another way you will have to understand linear time-invariant systems and transfer functions and convolution is in terms of frequency response and what it means. Hopefully later all these ideas will get tied together. Okay. So that's the picture there. When you look at the frequency response, the transfer function, and you plug in s equals j omega, so that's the frequency, that's the transfer function evaluated along the j omega axis. This is called the frequency response. You usually only give it for positive omega because you can reconstruct it for negative omega because that's just the conjugate. So that's easy to do. So let's look at an example. Here's an example. It's a low-pass it's a single pole transfer function, 1 over s plus 1. Impulse response is this decaying exponential. Sometimes people call that an exponential smoother. People call it a discount rate in economics. It has all sorts of different names. I guess in electronics you would call this a first order, a single pole filter, right? And you have a rough idea from 101. The step response is your old friend, this thing. That's your step response, and so on. So, so if I put an input in, which is cosine t, then what happens is this. To find the output, so here's the input. The input is the dashed line, okay? And here is the output of this thing, the dark line. You could work it out exactly using Laplace transforms, but I did it for you and plotted it here. And what you see is that the output is not exactly sinusoidal. In fact, if you look carefully here, you'll see that it takes about 3 cycles to build up to its full steady-state amplitude, okay? And for that matter, phase. But the point is out here, this height is about equal to 1 over square root 2, which is this thing evaluated for s equals j omega because omega is 1, okay? So the response of this thing to a sinusoid of frequency 1 is asymptotically another sinusoid, same frequency, magnitude 0.7 approximately, and a phase lead of 45 degrees, something like that. So, or phase lag, I should say, it's minus 45. I always find these diagrams extremely difficult to read. I don't know why, I still do it. When you look at this and you see the black signal and the dashed signal here, the solid signal and the dashed one, doesn't it look like the solid signal is kind of ahead? I don't know. I always think that. Okay. But the truth is it's not. It's the other way around. And I've always found this confusing. This solid signal here is actually lagging the other one. That's the idea. And the reason is it gets to the same point later. It's to the right, which is later. To the right is later. So that the relative phase shift is 45 degrees. I don't know why. I'm not sure why. I guess time axis goes from 0 to t, and I guess we read from left to right. I don't know. Don't ask. Actually, that works too. I guess if you think about reading this from left to right, you'd first encounter the dash signal, and then later the solid signal. I guess that still works. Okay, anyway. I usually just sit down and figure it out. Okay, so this demonstrates this idea of this asymptotic stuff. Now, more generally, if the system is stable and the input is asymptotically sinusoidal, in other words, it doesn't even start sinusoidal, but it builds up to a sinusoid or something like that, or just ultimately becomes sinusoidal, then what happens is the output also converges to sinusoidal, and the phasors representing the input and the output are precisely related by the transfer function or the frequency response at that frequency. So now you have another interpretation of the frequency response. The frequency response is the ratio of the phasors of the asymptotic sinusoidal output to the ratio of that to the phasor of the asymptotic sinusoidal input, right? So, for example, if this is a really large complex number, it says that system has high amplification for signals of that frequency. If it is always a small complex number, it says that all frequencies are reduced by that system. If this number, magnitude h of j omega, for example, is approximately 1 for all frequencies, it says that whatever that box does, whenever you put in a sinusoid, what comes out is a sinusoid of about the same amplitude. Okay? The phase can do all sorts of things, and that would be the case if the phase angle of this varies. Right? That's what that would tell you. So this gives you another rough idea of how these things work. So as some simple examples here, if the frequency response is large at a certain frequency, it says that the system is very sensitive to sinusoids at that frequency, to oscillations at that frequency. Okay? If you plug in omega equals 0, that's the DC gain, which we already know anyway. And says that if you have h of 0 equals 2, it says that if your input is a sinusoid with frequency 0, otherwise known as a constant, then it says that such sinusoids are amplified by a factor of 2. So that says if you put in a constant of a certain height, the output is also asymptotically constant with a height of 2. So this is the idea. Or as another example, if the frequency response falls for large omega, then it says that the system responds less and less to very high frequency wiggles and things like that. Okay, so we'll quit here, but this will be the I guess this will be now like the fourth or fifth way you have of thinking of a convolution system, and the goal is going to be to tie it all together.